All right, let's dive right into this explainer and demystify the somewhat complex world of modern apps. Look, if you've ever wondered how titans like Netflix, Amazon, or Uber just keep running so smoothly without catastrophic crashes, you are definitely in the right place. Today, we're breaking down the ultimate system design architecture, and we're going to use some simple, everyday analogies to do it. To really understand this, let's look at a classic comparison. Imagine you decide to open a restaurant. At first, it's just you in one giant building, right? You take the orders, you cook the food, you wash the dishes. In software, we call this a monolith. It's super simple to start, but imagine the utter disaster of your giant restaurant shutting down completely just because one stove breaks. Your dishwasher quits, and suddenly the food just stops coming out. But what if you broke your restaurant down into a food court? Well, that is exactly what microservices are. You've got one stall that only makes burgers and another that only handles drinks. If the burger grill breaks down, no big deal. It doesn't stop the drink machine from working.
So to truly grasp this cheat sheet today, we're going to follow a very specific user journey, buying a pair of shoes online, and map it through 4 critical structural layers. The top layer, communication and safety, shipping and upgrading, and finally, the honest truth. Let's get into it. Okay, to bring this all to life, let's start with the core concepts from our source material. We begin right where you, the client, enter the picture. You might be on your phone, maybe your laptop, or even a smart TV. From that device, you're sending a request to the app's brain because, well, you want to buy those shoes.
But here's the thing. Before your phone can go talk to 50 different tiny apps, it has to pass through the API gateway. Actually, think of the API gateway acting just like a luxury hotel concierge and a front door security guard rolled into one. It handles routing, telling your request exactly which way to go. It handles authentication, checking your ID to make sure you're actually logged in. And crucially, it handles rate limiting. That makes sure one person doesn't just spam the door and crash the entire system for everyone else.
Right, so once you're past that front door security guard, your request finally hits the actual microservices. And look at how they're broken down into highly specific jobs. You've got the user service, which is just managing your profile and passwords. You've got the order service, handling your shopping cart. And you have the inventory service. That one has literally one independent job, checking if your shoes are actually in stock.
Now, the absolute most important rule of this entire microservices system is database per service. Notice how every single service has its own separate database. The inventory database cannot touch the user database. They are completely 100% isolated. And this is a game changer because it guarantees that even if the inventory database entirely crashes, your sensitive user profile data remains perfectly safe and secure.
But what happens when Black Friday hits? Your app gets ridiculously busy and the order service gets totally overwhelmed. Well, in this architecture, the system just automatically clones that order service into 5 identical versions to handle the massive rush. But that raises a question. How do the other apps know where to find these brand new clones?
The answer is, services find these newly created clones through a pattern called service discovery. It acts exactly like a live phone book. As new clones are spun up, they constantly register their new phone numbers in this book, so every other service knows exactly how to reach them in real time.
Meanwhile, load balancing steps right in as the traffic cop. If you have 5 clones of the order service, the load balancer evenly distributes that massive flood of incoming Black Friday shopping requests across all 5. This ensures that no single clone is ever crushed under the weight of the traffic.
Now, safety is also built right in, because what if the shipping service just goes completely offline? An old monolith application would just stubbornly keep trying to call it, getting stuck, waiting forever, and eventually freeze the whole app. But our microservices, they use a circuit breaker. It simply trips like an electrical switch in your house. If a service fails too many times, it just stops calling it and instantly returns a safe error message, something like shipping temporarily unavailable, which totally saves the rest of the app.
And this brilliantly illustrates the bulkhead pattern, which works hand in hand with that circuit breaker. It's actually named after the partitions in a ship's hull. If water floods one compartment, those thick walls stop it from sinking the entire ship. In our system, it means one broken service won't sink your entire company. To keep things moving fast, these services don't sit around waiting on hold for each other. They use event-driven architecture. So instead of the order service calling payment and waiting on the line, it basically just shouts into a megaphone, "Hey, order 123 was just created." The payment service hears the shout, processes the card, and shouts back that it went through. Then the notification service hears that shout and automatically emails you a receipt. It's incredibly efficient. This fast-paced chain reaction of shouting is managed by something called the Saga pattern. It's an absolutely crucial piece of the puzzle because it ensures that a massive, multi-step transaction spanning across 5 different databases either finishes perfectly across all of them or it safely reverses itself if something goes wrong along the way. All or nothing. So, taking a step back, the crucial point here is how do developers actually package, upgrade, and monitor all these chatty, independent pieces without causing utter chaos? Let's dive into the next set of concepts. Well, first, they use containerization with tools like Docker. Think of it as a literal shipping container for code. It packs the code, the tools, the whole shebang, everything the service needs into one standard virtual box. This guarantees the service runs exactly the same way on a developer's laptop as it does on a massive Google or Amazon cloud server. Then, when it's time to upgrade, teams achieve zero downtime using blue-green deployment. They keep the current blue version running live, build the brand new update in a hidden duplicate green environment, and when it's fully ready, they instantly flip the API gateway switch. Literally zero downtime. And if they're replacing an old monolith, they use the strangler fig pattern, where they slowly chip away at the old system, one tiny feature at a time, until it just fades away. But let's be totally honest for a second. Finding a bug in hundreds of tiny apps, that's like searching for a needle in a haystack. That's exactly why engineers rely on observability. They keep constant logging diaries, and they use distributed tracing. Tracing assigns a unique tracking number to your click. If your payment fails, engineers can trace the exact path your request took across the user, order, and payment services to pinpoint the exact second it failed. It is for sure an absolute superpower. Okay, let's move on and see how this all builds into the honest truth. We really need to weigh the incredible, high-flying superpowers of this architecture against the harsh, heavy burden of keeping it alive. Because it's not just architectural style, it's a rigorous operational discipline. The upside? It's massive. You get independent deployment, meaning the checkout team can push updates 5 times a day without asking the profile team for permission. You get technology freedom. You want to write the AI recommendation engine in Python, but the inventory service in Java? Go for it. And you get pinpoint scalability, meaning you only pay to scale the very specific parts of the app that are actually busy. However, the painful trade-off here is the operational complexity. Instead of one app, your team is suddenly managing dozens or even hundreds. You face data consistency nightmares, constantly struggling to keep all those isolated databases perfectly in sync. And you have network latency, because instead of talking inside a single computer chip, these functions are communicating over the internet, which can really slow things down if it's not designed carefully. So, what's the final verdict for your system design? Well, it's highly pragmatic. If you are a tiny startup with 2 or 3 people, please do not use microservices. It will just slow you down. Stick to a clean, simple monolith. But when you have a massive engineering team trying to serve millions of users at the exact same time, you need microservices. It gives your teams the flexibility to move fast without breaking the entire company. Basically, if you are going to venture into this complex food court of an architecture, you must tattoo this golden rule into your team's operational discipline. Design for failure, automate everything, and make observability your superpower. So, as you look at your own engineering goals for the year and reflect on all the concepts we've explored today, you have to ask yourself a hard question. Is your team actually ready for the operational complexity of microservices, or are you just chasing a trend you don't really need? Let that sink in and keep